Okay, so today we have Monica Jinwoo Kang tell us about Emergent N equals 4 SUSY from N equals 1. Take it away.
Thank you for inviting me for this nice opportunity to talk to you. If I'll see you all in person soon during the summer. I'm going to start with a big warning that it is 8 a.m. here. So if I say something slightly with a mistake, please understand. And stop me anytime and ask questions. Today I'll mostly talk about the paper based on this, though there will be other paper previously that will appear for construction-wise here and there that led to this understanding. Today it'll be about building a dual theory that will give from the N equals 1 construction perspective that will give rise to emergent maximal N equals 4 supersymmetry. So, of course, I didn't say any dimensions there, as I think this particular meeting, I don't think I need to expect that it's a surprising thing to consider a 4D supersymmetric conformal field theory. Whereas in other places, now I have to usually motivate why I care about such high dimension as 4D or why I consider supersymmetry. But nevertheless, today I'm going to fully talk about in 4D settings, and most of the time we'll be talking about how the dual theory will give rise to a superconformal field theory. So 4D superconformal field theory can be then characterized by putting it on a curved manifold that the conformal symmetry becomes anomalous and will be characterized by two quantities, and we call them either conformal anomalies or central charges A and C, where it can be expressed as this particular expression. C is the one controlling the biodensers, and A is the one controlling the Euler density, which is actually the one that tracking the degrees of freedom of the 4D theory. In fact, most of the context today, it'll be really about taking Argyres flow and the emergence of the 4D N equals 1 to N equals 4 enhancement will be coming thereof. So what do you really know about these quantities would be that if you have a UV theory flowing to the IR theory, you can compare the two conformal anomalies, A and C. And what we know about the A theorem is that, as I was saying, it really tracks the degrees of freedom. And we can say that because we have A theorem, which always say that the A is monotonically increasing along this RG flow. Now, C, unfortunately, doesn't really have this nice property. It will mostly decrease along the flow, but not necessarily. But composite of this A and C will have some understandings that we can really think of. In fact, that will depend on the number of supersymmetry, what values it can really take as a ratio. And what I mean is that the ratio is explicitly bounded from the below and from the above as well, due to the unitarity of the theory, as we'll only care when the theory is unitary. If there is nothing else that we think of in mind other than just having 4D and conformality, the Hoffman-Malus-Sena bound will give us that A over C is bounded below by 1/3 and will be bounded from the top by 31 divided by 18. So we should think of like some scattering event that we can do in the conformal plane in the setup. So let's say there is some excitation happening and like in here, then all the operators that will be excited thereof will be then having excitation to be radiated throughout. So then this will then give us effectively energy flux through this thing that's going all the way at the infinity of the sphere, as we can have this plane of scattering event. Then we're not assuming any spherical symmetry of any kind. It can be jets of any kind as well. So then the dependence will be existing depending on which direction it goes. Let's call this as a direction of N. Then this vector dependence, the directionality, will be then determining how then we will have non-isotropic type of understanding that can happen from this type of scattering event. And that dependence is explicitly having a coefficient that's proportional to this term. And as you can see, this is a term that has C minus A involved. So then A equals C is a very special type that kind of looks like a symmetry, but clearly not quite. When such is the case, without any further restrictions at all, the flux in all directions is always all the same. So then the energy and charge really propagates isotropically at this type of given settings. So thus, can you imagine that A equals C is a very interesting property, and the property that we can really look into, and that can give rise to something maybe beyond as a more symmetry enhancement of some kind. In fact, A equals C is always guaranteed for N equals 4 super Yang-Mills perspective, and also for N equals 3 super conformal field theories. But as it's not so surprising, we would expect that as supersymmetry is maximal, you'll have the most stringent type of restrictions that we can have. So then it'll decrease, and we'll have more windows that's allowed as it goes down with lower and lower number of SCFTs. But don't forget that A equals C happens at this N equals 4 super Yang-Mills setup. And whenever there's that enhancement, and this will really then give you a hint that maybe that's the special property you should try to consider to get such an enhancement to be possible. So this was the Hoffman-Waldau-Simon bound with no supersymmetry involved, and this was the A equals C bound. And you can get with a different number of SCFTs, we can get different bounds. That's bounded by free scalar Carl and hyper, and bounded above by the free vectors. And if you noticed, of course, that A equals C will be possible in the window for all of them, as A over C will be equal to 1. Now, supersymmetric field theories are really highly constraining, as I feel like this will be a particular crowd that I'm preaching to choir. I think we all appreciate why we're really dealing with supersymmetry and why enhancement will be so interesting. And it usually allows us to have things such as non-renormalization type of theorems, and further it protects certain quantities that are to be exactly computable, and thus that it brings rise to rich mathematical structures. Now, supersymmetry is always traditionally regarded as a high energy symmetry in the UV, but of course, it can also rise as an emergent symmetry in the IR through this type of RG flow, as I was slightly trying to emphasize in the very beginning. In fact, we learned a lot about the renormalization group flow using supersymmetry, and in many ways, we learned a lot about the IR duality, conformal manifolds, symmetry enhancement, dangerously relevant operators, non-commuting flows, and many others. In fact, we will discuss a lot of those today through this enhancement from N equals 1 to N equals 4 supersymmetry that we can get through this RG flow. Now, emergent supersymmetry is usually the best that we can do, as when there's nothing, then it becomes a more supersymmetric theory. Then we'll really then look into what can give rise to quantities that can really given through this properties. In fact, in 2 dimensions, supersymmetry has been shown to emerge in the dilute Ising model at the tricritical point already way back in the days in 1985. And this has been further extended to quantum critical points of higher dimensional lattice models explicitly at 2006. And as the talk is going to be really about N equals 4 enhancement, let's look at what we have seen, something like that in the very early days. In fact, really long time ago, like 1984, for these super Yang-Mills is suggested to arise from the strong coupling dynamics and the low energy limit of a non-supersymmetric gauge theory. And these are clearly the ones that was from non-supersymmetric to really a supersymmetric. But also, of course, we heard of Lee Stressler. That was the first really known example that found from the N equals 1 theory in the N equals preserving conformal manifold through marginal deformation to give rise to 4D N equals 4 super Yang-Mills. In fact, we're living in like a modern era where things are really suggested that you can see the emergent supersymmetry, hopefully in the experimental setup, such as the model that was discussed as that by Grover, Sheng, and Vishwanath, a supersymmetry can emerge at the edge of a topological superconductor. And that would be super exciting if such can be actually detected. Now, these are all sorts of amazing emergent supersymmetry models that has been existing throughout, and that's super exciting. But today, what we're going to do is using specifically the other renormalization group flow. So we can begin with the minimal supersymmetries, as though it's N equals 1, and flow to an enhanced supersymmetry in the IR. Now, enhanced supersymmetry then involves N equals 2 to 4 that we can have in 4D. And there are enough several known cases that are constructed by from an N equals 1 theory that's flowing to an N equals 2 theory. And usually for these cases that this provides effectively the n equals 1 Lagrangian descriptions that we can utilize for the n equals 2 non-Lagrangian theories that has been notably studied in these 4 papers and several others. So it's really not only an interesting phenomenon itself, but really provides a powerful tool to analyze this non-perturbative dynamics of the IR fixed point, which often really have no Lagrangian descriptions. I mean, even today, we're going to have all the non-Lagrangian theories that we're going to deal with, and the theories that we're going to really deal with, and with the full extended supersymmetry manifest. So throughout how we're going to build this will be then the supersymmetry enhancement in these cases can be thought of as another example of IR duality. So then really our task is using the IRG flow, we construct an n equals 1 non-Lagrangian theory that will be dual to the n equals 4 super Yang-Mills. And just to give you the answer first, this will be the dual theory that we're going to be able to construct and demonstrate that this will be indeed the case. So this is the theory that we're going to have. So there is some for the n equals 1 non-Lagrangian theory that we'll have to construct. And this is for the n equals 1 just theory. And so it'll have the RG flow down to a super conformal field theory and the IR fixed point. And through here, we will now detect a marginal deformation that will go straight into the conformal manifold of n equals 4 super Yang-Mills, which is lying in the full same n equals 1 preserving conformal manifold, and thus that they will be explicitly dual to one another. And this for the n equals 1 theory actually has A equals C. As I was leewaying in the very beginning, A equals C is looking like some sort of symmetry or can be exposed as such when we freeze in the manner of how it was giving isotropic energy flux from a conformal scattering event. So then we're going to really have then this A equals C. By the way, this is not taking large n limit. This is in the finite n sense as A equals C. And for the n equals 1 theory, and we'll flow it directly down so that it can be shown dual to for the n equals 4 super Yang-Mills. So then what we really have to do is constructing this n equals 1 theory with A equals C. And as you notice, there are 2 ingredients explicitly. So there will be these theories. These are called DPG theories, and we'll be diagonally gauging to have a vector node. So first, what is a DPG theory? So individual DPG theory is a for the n equals 2 superconformal field theory. So that we're really using this n equals 2 description as individual building blocks to construct the n equals 1 theory. So these are individually Argyres Douglas type, and it can have at least with a flavor symmetry that's at least G given by coming from the regular puncture, but it can be enhanced further depending on the regular puncture data. So the n class S description, since we live in a modern world, I'm going to use the class S description throughout the talk. So this will be the regular puncture that carries the flavor symmetry G, and this will be another puncture that's irregular. So then the flavor central charge coming from this theory is effectively given as this, as you can see, that has the flavor symmetry. So that if irregular puncture is not enhancing anything, it'll be just giving that exactly matching just that contribution. But if it is not the case, we'll always have it modified to grow to a slightly bigger flavor symmetry. Now, A equals C actually happens when flavor symmetry does not enhance by the irregular punctures. By that, I mean really exactly will be flavor symmetry G without any additional factor of U1s or anything. And those things will happen depending on the choice of the G as this. And the one that we will really need to look into is this SUN part. And as you can see, no additional symmetry happens when P and N are coprime. And by having D2, then SU have to be N has to be chosen as odd. And if you remember, that is actually the model that we've constructed with today. In fact, I want to say that since we're having D2 SU odd in the end, when P is equal to 2, this flavor central charge is then, this is just becoming a factor 1. And so exactly just HG check, regardless of the choice of the G. So then this will effectively now, if you look at it, just KG is equal to HG check. So it really behaves like a fractional amount of an adjoint matter is what we really get. So what we're going to do is having now taken the 3 copies of D2 SU odds, and then we'll now have a diagonal gauging the flavor symmetry group. And we're going to do that by explicitly by n=1 gauge multiply. So by gauging in n=1 sense, in the end, this theory will be an n=1 theory, as we'll have our symmetry broken down. Now, this will give now as an asymptotic free gauge theory that will flow to the superconformal field theory through the IR fixed point, and that'll flow to now a point on the conformal manifold of n=4 super Young mills with SU odd. Now, how do we verify this novel duality? We're going to do it by matching 3 different things. We're going to first match anomalies. We're going to match chiral operators, so thus operator spectrum, and matching superconformal indices. Yes?
Yeah, do you know in advance why it's using 3 in particular copies of the conformal matter is what you want to do? Or is it just a matter of trying different combinations and see what gives rise to an interesting flow?
We will get to that actually in the end. Can I reserve your question and answer?
Yeah.
It's more like nearing in the end. I wanted to go to more actually construct these more difficult reasonings in the end.
Okay.
Perfect. All right, so then we'll first start with, of course, matching anomalies and describe why we can get such things. So as I was saying, we're going to do diagonal gauging. So then we should check first, as a supersymmetry field theorist, check the first 1 loop beta function coefficient for the gauge coupling. So then we can get this trace RGG with a minus sign, and we can see that this will be then explicitly negative. So it's asymptotic 3, and it's IR strongly coupled, so it naturally flows to the superconformal field theory IR fixed point. So then it really looks like in this particular setup that this D2 this SU odd or D2G really behaves like a half of an adjoint chiral multiplet in terms of this 1 loop beta function contribution, namely just NF is 3/2 of NC. Now this, as I was telling you, it's gauged in the n=1 sense, so it'll really break the symmetry. So in order to really understand the symmetry structure before doing anomaly matching, we'll have to actually see in how it'll give rise to the symmetry we desire and what we can compute coming from for the anomaly coefficients. So individually, they're n=2 theories. So you're gauging diagonally. So you're gauging the flavor symmetry part over here. So then it'll break it into n=1 setting, and it'll give rise to this. Now combined naively will just give you this G, that's the SC2n+1, and then you have the U1, the R symmetry type, and then the flavor symmetry that looks like naively a cubed. And this will be the generator that'll be mixing coming thereof. So this small r is the part that's the U1R charged to the n=2R symmetry. So it was originally this one. And this I3 is the SU2R Cartan part of the n=2R symmetry. So it is the other type of the R symmetry that we had here. However, this is not actually correct because upon gauging, only the anomaly-free combinations are preserved. And in the IR, this U1 cubed has an ABJ anomaly that will be broken to the anomaly-free actually U1 squared. So I'm going to take as the IR theory to have the curly F to denote as this new flavor symmetry, because that was a UV theory that we had before the RG flow. Now, all we need really is to have this U1R symmetry to make sure this is the n=1 superconformal field theory. And that's the only necessary condition we really need to have. And in a supersymmetric field theory, conformal anomalies are fixed by the trace anomalies of the R symmetry. So we can write A and C as this. Now, then we now have a family of candidates for what's the correct R symmetries. And this can be entirely fixed by fixing the R charge or the mixing parameters. This to be determined uniquely by the A maximization, so that through this protocol, we'll be able to explicitly find the R symmetry, and thus we can get the conformal anomalies coming from thereof correctly. And further, we can check if the theory is unitary upon the RG flow by this A maximization. Now, putting this together, I put that in green right here so that you can actually see how that will gonna go. So then the anomaly-free, the actual symmetry structure we're going to have is, now I'm going to put it as a new R, that's going to be mixing from this R naught and all the flavors. So this is going to be the A maximization uniquely determined. And this will be the leftover U1 squared that you're going to have. And this F has two things, that's combinations of original three different Fs. And of course, the anomaly is trace RGG, and this is going to be our now IR flow in N=1 superconformal field theory. Now, as I was saying, then the R symmetry is then given as just this with that mixing parameter. So using the anomaly-free condition, then you can just compute and what that would entail. And this will give rise to this condition as the mixing parameter. And then the A maximization will then fix this mixing parameters. So this is the A function as an ansatz, and you can see that this will be maximized when all three of the epsilons are identically minus 1/3. Now let's input them directly to what we know here together. Then the central charges we're going to get is exactly the quarter of dimension of the SU odd, and that'll be what we're going to have. Now, it must look really familiar to everyone. That was the N=4 superior Mills central charges. Now, let's put them all together. So the anomaly polynomial of this IR theory after flowing is given as all this. It's two lines with all the anomaly coefficients that it can have. Now all the rest are 0 except these. Now D is exactly this dimension of the SU2n+1, so that's 4n n+1. And the rest can be then explicitly given coming thereof with this, because these are combinations from our symmetries and the vector node as a vector multiplet, so we can compute them explicitly. And this is the simple chart we just checked right above. The rest will be explicit now depending on the same factor. And this will match exactly of those of N=4 superior Mills with G SU odd. So that now we did check these, and then the two anomalies are invariant on a conformal manifold. So what can really deduce coming from that is that this IR theory really lives in the same N=1 preserving conformal manifold as N=4 superior Mills. So we're already done with the first check. They verified the matching anomalies work really perfectly. Now let's do a little bit better. So let's now try to match now chiral operators. By that, I'm going to compare the gauge invariant operator spectrum of the dual theories. So let's look at from the N=4 superior Mills perspective. The single trace chiral operators of the N=4 superior Mills is given by these, and individually these are adjoint chirals. And I'm putting as 1, 2, 3 to name that there's 3 different D2 SU odds. Now, that's from the dual theory perspective. Each D2 SU odd has the moment map operator mu in the adjoint of G with dimension 2 and carries the R charge to be the R = 0, and this is the I3 = 1. This is the U1 carton of the N = 2, and this is the SU2 of the R symmetry in the N = 2. And this G is SU odd. Now, as I was doing, we were going to now do the RG flow down to see what it went to the IR theory from N = 1. And the moment map operators in the IR then will just compute this and give us exactly 1. So that's going to be matching really well with this. So upon gauging, now mu, mu2, mu3, because there are 3 copies of the 2 SU odds. Now only the singlet part will survive, so we can just get this particular thing that'll be matched explicitly coming from this in the N=4 superior Mills. Now, let's look at now what's going to happen with the Casimirs and the Coulomb branch operators. So each N=2 multiplet containing a Coulomb branch operator has 2 N=2 chirals, whose components are then this scalar primary that I'm going to call as U, and its n equals 2 descendants, that's Q squared U. Then each D2 SU odds has Coulomb branch operators of scaling dimensions of this, because it's just going to be R over 2. And this will be the ones that we're going to have, all the odds divided by 2. And their super partners come from the Q squared U. And that will give you as this plus 1 in the scaling dimensions. And that will be minus 2. And this will be now 1. Now, upon the RG flow, now we'll have to look into these two operators in the IR. So then through mixing parameters, which epsilon was 1/3, minus 1/3, we can get these, which if you plug in the epsilon equals minus 1/3, it'll give you 2, and that will be 2, I think minus 1 plus 2 of this. Now, in putting them together, now then we're going to really have the spectrum of all the integers coming from 2. That looks like it's going to match explicitly the Casimir operator of the n equals 4 super-Yang-Mills, which is just given as the this. So that now we can understand the Coulomb branch spectrum of the this IR theory will match explicitly with the Casimir operator, which will be the one that's corresponding to as the Coulomb branch operator in the n equals 4 super-Yang-Mills. So summarizing them together, we have now operator spectrum matching as this to this, and that to that. Perfect. And all the superfluous looking chiral operators are removed by chiral ring relations of these two. So what this says is that the adjoint part of the square of the moment map is vanishing. Now, what this means is that this is true because the Higgs branch of the theory is given by a nilpotent orbit. So thus this removes the superfluous Casimir operators in the spectrum. Now that we matched the explicit chiral operators, we should also check that if the conformal manifolds are matching between the two theories. So in the dual theory of n equals 1, it has 5 marginal operators, but there's 3 coming from directly from each Coulomb branch operators of the lowest dimension. If you remember, that was 3/2. And then there is additional 2 that's formed from moment map operators of just 1, 2, 3 and 1, 3, 2. They're different. Now, among them, 2 are marginally relevant because it breaks the U1 squared symmetry. So they combine with the broken flavor symmetry currents to form a long multiplet and will become non-BPS. Now let's look at the for the n equals 4 super-Yang-Mills side, which has 11 marginal operators of this form. We can definitely do arithmetics at 8 a.m. today. And among them, 8 are marginally relevant, because they recombine with the generators of the SU3 flavor symmetry, which will be broken at a generic point of the conformal manifold. So in turn, 11 minus 3 is definitely 3. So the conformal manifold is 3-dimensional, complex dimensional from both, and they, my bad, and they're matching. 1 moment, let me find that one. Right. Now, that was perfectly matching. Now, let's check if that will match with the U1 squared preserving sublocus. So I'm moving to this then U1 squared preserving sublocus of the conformal manifold. The off-diagonal generators of the SU3 current combine with the marginal operators to become long multiplets and become irrelevant. And this will remove 6 out of 11 from the n equals 4 super-Yang-Mills side. And of course, this side is not going to move anything. It had 5 marginal operators. So they both give 5 dimensions, so they perfectly match as well. So now we have checked all the chiral operators are matching. In fact, you're already done with 2 out of 3 checks that you can do, and we've been having a blast, great matching between the 2 theories. Now let's do a little bit more sophisticated check. I want to really now then match the superconformal indices. So for D2 SU odds with n bigger than 1, meaning SU5 and above, you don't really know the full index. So that would be impossible to really compute. So the only case that is really computable from the known understanding is D2 SU3, which is the lowest limiting case that we know coming from this. Now, using this, we can compute the superconformal index of this dual theory, and it'll give you like this. Now, J1 is J2 is a Lorentz spin That's our symmetry, and that's the flavor symmetry. So those are the fugacities accordingly. Now this will match that of n equals 4 super-Young Mills with SU3. And I definitely did not write this for you guys to read it thoroughly, but this is the result that you'll get up till the T to 10th order. So we checked pretty thoroughly. As you notice, we use the SU2 and SU3 as the character representations. Now this one is having this Y elements there because that's the one in the Lorentz spin, J1. And the U1 squared flavor symmetry enhances to SU3 at certain points of the control manifold. So that's why each term is written with respect to now SU3 of their representations accordingly so that we can match it. That's great. So we have super conformal index matching for one case that we can really do, but that's not satisfying. We want to at least check some sort of things can match as a spectrum perspective for overall all the D2 SU odds that we constructed. But while we cannot really get the full index, we could at least look at a special limit. So we're going to look at the Shor limit of the index and compare the two. Now, if there existed a full index for D2 SU odds in general, the index of this dual theory would have been written as this, and that's the mixing parameter we found from the A maximization earlier. For the individually D2 SU odds, then the Shor limit is known, and that's why we can compute it, is this. So what we're going to do is we're going to use this and then compute the overall theory as the Shor index by pushing into that limit. Now this is identical to that of a free hypermultiplet upon rescaling Q to Q squared. Now let's look at the n equals 4 super-Young Mills side. So index of this n equals 4 super-Young Mills is given as this, and this is coming from the Adrian-Karl contribution. So the index of the Adrian-Karl is simply just given as this. And as you can already kind of tell, it looks really similar, except just this factor. And that will be exactly the case that will be taken care of by taking to the Shor limit. You can take to the Shor limit by looking into this. Now change this Q into PQ1 cubed by taking this. It'll look exactly the same. So thus, we'll have this Shor index of the dual theory matches explicitly the Shor index of the n equals 4 super-Young Mills for all constructions that we have thus far. So nevertheless, that we couldn't compute the super conformal index for all the higher cases, we at least know the Shor limit that they are all matching, and the lowest limit is matching entirely with the full super conformal index. So then all three of them are explicitly matched. Voila, we've done it. So we can safely now claim that this is indeed the dual theory for the n equals 4 super-Young Mills. Now, you would probably be curious, what if we consider anything that's beyond the SU odds? In fact, why did we pick that particular scenario that was giving you that particular setup? And I was telling you that it was having A equals C without taking a large n limit. Because in fact, this is one of the cases that can give rise to A equals C theories and how we can really utilize to take with a manipulation that we can do thereof. Then what's really important to check is how do we construct the n equals 1 or 2 supercontrolled field theories with these A equals C in this fashion. By that, I mean having DPGs and then gluing in together without taking up flavor symmetry enhancements at all coming from the individual DPGs. And then for those, then can we also see that if there is any connection with n equals 4 super-Young Mills that's beyond just what we just saw as a giving direct dualities to n equals 4 super-Young Mills. In fact, then let's look at this was a special example of theory that you can have as n equals 1 that has A equals C. Let's construct them overall in that fashion. So what did we do? We took a collection of DPG theories, and then we just gauged together as diagonal gauging. Now, let's first consider the easy case of n equals 2 SCFT so that we don't break the supersymmetry. Then we require the 1 beta function for the gauge coupling to vanish. Then this will be the explicit one that we have. And remember, these are the central charges of individual DPGs. And to satisfy this, and this is the requirements that we have. Now, there's exactly only 4 solutions that are those, and it also happen to match solutions of things that we can construct like this. So individually, we can have 4 different solutions that have this type, and then we can see that they're explicitly A equals C. And this G has additional requirements that the theory is only A equals C when the largest comark associated with this linear diagram that's coming from what it gives rise to as a shape when it's taken as an affine diagram. So for example, if you take SU D2SUN, SU2N, and this is, and the coprime has to be taken with this and the dual Cox number of the group that we were taking. And these theories have no flavor symmetry enhancements, so that these are all possible theories that we can really have. And note that by construction, this theory has at least 1 exactly marginal coupling, and the theory has 1 form symmetry given by the center of G. So it really says a lot of information that we can really have as a structure that we have possessed coming from here. One of which that's more striking that we can have, because you're about N equals 4 superunion connection, these theories that we construct have identical Schur index with the N equals 4 superunions upon rescaling fugacities, like as a largest comark, and that over 2 minus 1. In fact, this is true beyond just the A equals C theories, because there's a superset theories including these, as it's not just this and this. These 2 are the A equals C theories, and it also works for those, because this happens as long as there's no flavor symmetry enhancement for individual DPGs that's constructed in this format. But that really already hints a lot of that we have N equals 4 superunions beyond just the enhancement, but further on to overall A equals C theories. In fact, we can do a little bit better for a specific case that's constructed for 4 copies of DPGs. So remember, this is the one that had required 4 copies because it needed this. The rest are trinians. And for the 4 copy theories, we can actually compute the Schur index to be matching that of the McMahon's generalized sum of divisor function, which is quasi-modular, and can show explicitly also that it'll have then closed form formula thereof. So that hints that maybe all the other things can maybe quasi-modular, but we cannot say for certain because the series is not something that we can really detect to know at the moment. Now that was the N equals 2 construction, but let's do actually better that consisted of the today's dual theory example. So how do we get the for the N equals 1 theories with A equals C was that we're gluing all the DPGs and gauging with respect to G. But now this is N equals 1, so we should now consider the conformal gauging as beta equals 0, and also beta going to negative. And in fact, our case was exactly onto this, that it was asymptotic free, and then it just flows to the superconformal field theory R fixed point. So then this will really impose the condition to be given as this inequalities to be satisfied, which now there will be not 4 cases, there will be a lot. In fact, these are all the cases that we have to do. All the ones with the P's that has no numbers, but the letter is anything beyond, anything involving 2 or beyond. So there's infinite families of systems that we can satisfy to give rise to N equals 1 superconformal field theories with A equals C, or the one flows to N equals 1 superconformal field theories with A equals C. Well, not all gaugings flow to interacting SCFT, so this one is then spread out. And if you look at the next example, this is what really gave the dual theory to N equals 4 superunions today. We took individually these 2 as 2, 2, 2. So that this is actually one of the examples we could have explicitly constructed that can be given rise to having this A equals C theories that we can do. A surprising fact here is that for all of them, when we satisfy the same condition that we gather from the N equals 2, we still always have A equals C manifest and can be shown without even doing any maximization or anything. It'll be just enforced by construction itself, which is really surprising that we can get such a thing. Now, then this is like one of the simplest theory that we can really do, and without having additional matter coupled to it another. So that this is then the natural candidate that we could have hopefully tried to have the dual theory to flow down to as n equals 4 super Yang-Mills, and that's what we really checked earlier today. Now here we can also now include more adjoint matters up to 3, because we can satisfy the same condition by adding them. And for those cases, in fact, taking the philosophy that we learned from the n equals 2 constructions by taking just this largest comark and a dual Cox number to be co-prime, and the matter to be fully adjoint, will then manifestly make sure that A equals C is intact and robustly there without doing any additional operations, so that the anomaly cancellation is all condition that we need on top to guarantee that we still have A equals C theories. In fact, that means that we can really deform by these superpotentials and try to do all the landscape of n equals 1 theories with A equals C, like inspired with the SQCD with 2 adjoint Carl's analysis from interligator wet. In fact, we can do and analyze all of these things, and all the superfluous things that comes thereof can be used a flipper field to get it removed. So that, but those will be then no longer A equals C anymore. But we can now understand as a landscape as overall, we can do that with both 1 and 2 adjoint Carls. Now we don't do 3 adjoint Carls, that'll give you exactly n equals 4 super Yang-Mills. In fact, during this process, what we find is that it turns out many, of course not all, of the A equals C theories we consider can be deformed so that it really already flows to the n equals 4 super Yang-Mills theory. So that what we considered really earlier today was a particularly great example that demonstrates this as a marginal coupling case, but it does not, and then what we find here is that from deformation, we also find additional many theories that actually flows directly down to enhancement of n equals 4 super Yang-Mills. Now, upon deforming these individual DPGs via the relevant operator of scaling dimension of p plus 1 over p, it flows to a theory of just this dim G of the rank G of the 3 Carls. So by deforming our n equals 1 and 2 A equals C theories that we've constructed thus far using this particular operator, then we can really effectively reduce this DPG theory via an adjoint Carl and G. So then once we really reach 3 adjoint Carls and nothing else, we get a theory that is in the same conformal manifold as n equals 4 super Yang-Mills. So then you can imagine of having this type of operation, and you can then tell that a lot of the theories of the A equals C will then manifestly really give rise to this type of theory that we're going to have to be containing the same conformal manifold as n equals 4 super Yang-Mills. So then what we really saw was like a very putative understanding that will be really effectively understood as manifestly that will be systematically doable from looking into A equals C theory constructions. In fact, this is really fascinating because while doing this process, we are not only seeing the enhancement of n equals 1 to n equals 4, but n equals 1 to n equals 2, and vice versa continually. So we can have landscapes of having just the added 1 adjoint Carl as overall together, and also added 2 adjoint Carls together, and then how it mixes the number of adjoints throughout this process. So you can have a really holistic, huge pictures that's much, much, much bigger than this picture, so that can be understanding everything together, with a lot of them ending down to n equals 4 super Yang-Mills after all. Now, A equals C theories are really interesting because A equals C was actually particularly the quantity that we want to see from many different aspects, but mostly also because it's really interesting from holographic aspect. Now, when you put ADS5 dual, generically, when you have holographic dual theories, that it requires at least A equals C to be explicitly identical in the large N limit at the very least to have the supergravity dual. And when you do that, in the supergravity action, you're going to have the 4 derivative terms so that are effectively square term. And that will be explicitly giving you the correction term. And that's having a coefficient that's proportional to C minus A. So that would vanish in the large N limit. And that's how we usually got those theories. But note that here, the theories are actually A equals C without taking any large N limit. So what it means is that even if you're taking the finite N, this supergravity action will not admit this R squared correction term, as the coefficient will vanish. What that really entails is that we would really then expect for these finitely A equals C theory to have also all the theories to be have supergravity duals, and we can expect to maybe able to build such a thing to be the case. So then the A equals C theories will be then a one way potentially to have holographically dual admitting theories that we can construct through this format. And that would also be then explaining how it can be understood as something that's from holographic understanding with the N equals 4 super Yang-Mills perspective. So the aforementioned class S description really paves the way to a holographic dual of N equals 1 theory, really in the UV, and having these all the 4D N equals 1 and N equals 2 theories at A equals C, then we can really try to now match this to have put holographic duals and try to understand what that means to have that to give rise in the RG flow to the 4D N equals 4 super Yang-Mills holographic dual solution through this flow. So what that really suggests in the holographic picture is that there must have been a domain wall solution that really interpolates the N equals 1 theory as a UV theory, and in the IR that flows down into the N equals 4 super Yang-Mills dual theory. And we all know that in N equals 4 super Yang-Mills theory, there is miraculous cancellation that happens. So what that means is that we're going to really understand that maybe a hint is that we're going to have understanding of this seemingly fine-tuned coefficient that we can have, and perhaps using this N equals 4 IR duality to learn more things of the structures that we have that we couldn't have seen in the N equals 1 theory, and also N equals 2 theory potentially as well, all together. Thank you for listening. I'll answer any more questions if you guys have.
All right, let's thank Monica. Do we have questions?
I hope I answered Philip's question earlier.
Yes, definitely.
Perfect. I'm kind of concerned that there were no questions. I hope I didn't go too fast.
Maybe it was just very clear.
I have a
go on.
Question. You mentioned in passing dangerously irrelevant operators and said that they would make an appearance, but maybe
yes. Oh yeah, because when I made that slide, I want to also include the our papers that analyze all the theories and with the operator spectrum perspective. So we have computed operator spectrums for individual theories of the 4D N equals 2 super conformal field theories with A equals C. And we have found that how it actually gives rise to class S description for a particular case, which is also the same, the 4D-PG glued-in theory, the one that gave rise to the McMahon sum of divisor formula, also can then with respect to have a class S description, whereas other ones we couldn't really have a class S description known in the literature to be done. And this you actually needed a twisted Z2 twisted punctures to be constructed with the 2 as a and then glued in, so that's a pair of pants decomposition type of picture. And what we found is that there's actually the D hat multiplets in terms of Dolan-Osborne notation, so that it's a Littlewood index and the Higgs branch Hilbert series don't actually really match. And we also compute irrelevant operators and what things can really go wrong beyond just the relevant operator spectrum. So I was thinking of mentioning that when I wrote that, but I actually didn't.
Okay, I will. I guess I should look at your papers.
Or, well, I'll answer any questions if you have as well.
Okay, do we have more questions? Well, I'd say then let's go off the record after we thank Monica one more time.
Thank you.